So, stepping back and looking at the big picture here, in this scenario, we've given this bar some initial kinetic energy, let it slide to the right, inducing a current here. That current is going to be dissipated as heat in our resistor over there. So basically, we're powering this resistor. It could be a lamp or any other device, and by giving this bar a push, we're powering it. So we're converting motion into electricity, converting kinetic energy into electrical energy that's dissipated as heat right here. We've got a generator. That's what a generator is. It's a machine that converts motion, kinetic energy, into electricity. So we've built a generator, and it required Faraday's law of induction to do it. Electromagnetic induction is the key behind the key principle that makes electrical generation possible. So let's take a closer look at the details of the energy transfers in our generator that we've got here. I'd like to know what does happen to that initial kinetic energy we give the bar when we give it that initial push. What happens to the K? We know the answer. It must be dissipated as heat in the resistor, but you might be skeptical about that. Like, how much of the energy is dissipated as heat, for instance? All of it or only a portion of it? Does some of that kinetic energy go somewhere else? We can verify this. What I'd like to do is try and compute the total energy dissipated as heat in that resistor as time goes from 0 to infinity. So give that bar an initial push. We know that it will take forever to slowly slow down and come to rest. So during the course of that whole time the bar is sliding, there is current circulating, dissipating energy as heat. So as time goes to infinity, how much energy ultimately comes out as heat here in that resistor? How much energy are we supplying to our device over here via our generator? Okay, so the rate of energy dissipation in that resistor, we call that power, the power output of that resistor. And it is the current through that resistor squared times the resistance of that resistor. So I squared R, that's the instantaneous rate of power generation or power dissipation in our resistor. So since that current is a function of time, the power output will also be a function of time. Rewriting that equation this way, we see that in an infinitesimal amount of time dt, when this small amount of time passes, a small amount of energy is converted to heat in our resistor based on the instantaneous current in that resistor and the resistance. So this is some small amount of heat generated in some short amount of time. We want to add up all the heat generated over all time as time goes from 0 to infinity. So the total energy dissipated, if we wait long enough, will come from integrating this expression as time goes from 0 to infinity. And we're going to substitute in now our function for the current as a function of time. And for I of t here, we've solved for this function earlier. So here it is. We know that current the induced current in our loop will depend on the instantaneous velocity of the bar. So v is a function of time, I is a function of time. This whole function is going to get squared here. Let's pull out our constants. The negative will get squared out, and the BL gets squared, R gets squared. That's the resistance. But there's an R up here and an R squared down there. One of those factors of R will cancel. So pulling out those constants out front here, BL squared over just R, because R squared and R. And we're left with the velocity as a function of time squared dt. We're going to integrate that. Fortunately, we also now know the velocity as a function of time. We solved for that. This is our exponential decay function for the velocity of the bar as a function of time. So this function is getting squared, and we're going to integrate that from 0 to infinity. Okay, so the Vx gets squared. E to the minus t over tau squared becomes e to the minus 2t over tau. That gets us here. So we pull out the Vx squared. I'll package that Vx in with the B and the L. All those get squared. One factor of the resistance down here. And 0 to infinity, e to the minus 2t over tau. We're ready to integrate. Our antiderivative will bring out a factor of minus tau over 2. This brings out to minus tau over 2. Then we have to evaluate our antiderivative from 0 to infinity. Checking that, we find that that just gives us a minus 1. That's great news. That minus will cancel that minus right there. So it's a positive amount of energy overall that we're dissipating. Almost done. So note that what we've got here is a 1/2 times tau times this, the BL Vx squared over R. That's our initial V, Vx initial right there. And okay, it doesn't look like much at the moment, but we do have an expression for tau. Tau was the resistance times the mass over B squared over L squared. Let's sub that in. For tau here, this is our tau, Rm over BL squared. And now, beautifully, resistance cancels, B squared cancels B squared, L squared cancels the L squared, and we're left with a 1/2 the mass of the bar times its initial velocity squared, or 1/2 mv squared, the initial kinetic energy of our bar. So how much of that bar's initial kinetic energy gets dissipated as heat in our resistor? All of it. All of it. This is an ideal generator. If there is no friction in these bars, in these rails here, as our bar slides along, there's no frictional dissipation of heat, then all of our energy we give to the bar comes out in our device over here. So there we have it, electrical generator converting motion into electricity.